is the final video for the straight line graphs chapter. This is about modelling with straight lines. So we've already done a bit of modelling with the quadratics back in chapter 2. Here we use straight lines to do our modelling. So we've hopefully already said that a mathematical model is an attempt to represent some real life situation using the mathematical concepts that we know. Sometimes we need to make assumptions about it in order to create a model that works, something that we can actually create. So if it's a model of a straight line, then the variables will be related by the straight line equation, y equals ax plus b. So we're not using mx plus c here. We're still referring to gradient and y-intercept, but we just use two different letters instead. So we can still use a straight line even if the points don't lie directly on the line, but they should be as close as possible. So if the pattern is clearly not a straight line, then we shouldn't be using a linear model. Something from GCSE is about direct proportion. Two quantities are in direct proportion if they increase at the same rate, and if one of them is 0, the other one is 0. In that case, there won't be a y-intercept other than 0, so it will be in the form y equals kx, where k is the gradient. So for every one increase in the x direction, the variable on the y direction increases by k. And this is other ways of noting that y is proportional to x. This is the direct proportion symbol, or y equals kx, as I've just said, with some real constant k. So there's just 3 examples for these. First one is regarding the extension of a spring. This is a common example, sometimes used in physics as well in the past. The extension of a spring when different masses are attached to it. So the heavier the mass that is put on, the more this spring extends. Calculate the gradient k of the line. Well, we've done plenty of that, finding gradients. We're just looking for change in y over change in x, and the bigger the triangle you can find, the better. So I'd be looking here. So my change in y there is 20, change in x is 400. K is 20 over 400, or 1 over 20. B. Write an equation linking E and N. Well, this is going through 0, so it's a direct proportion graph. There's no y-intercept added on. It's literally just in the form y equals kx, i.e. it's y equals 1/20th of x, or just x over 20. Of course, I've used y and x there. I should have used E and N. Stick within the context of the question. So it should have been E is 1/20th of m, or m over 20. Part C. Common question is to interpret what part of the equation means, what some coefficient might mean, or some constant might mean within the context of the question. Here, explain what the value of k represents in this situation. So k is how much the spring is extending every time m increases by 1 gram. So we put that into words. So k represents the extension spring in centimeters each gram of mass added. Okay, for each single gram, E represents extension in centimeters. So we know that for every gram we add, the spring extends by 1/20th of a centimeter. Okay, so that's the first one. Fairly straightforward. Go on, right. Right, example 2. Container has been filled with water, a hole put in the bottom of the container, and so the water is leaking out, and the depth of the water is being recorded at these time intervals, not regular intervals. That is to determine whether a linear model is appropriate by drawing a graph. So I have an axis here. Zoom out so we can still see the table. Okay, so we've got our depth of water against t, time. Time needs to go up to 120 seconds. So, by the way, I've set this up. This can just go up in tens. In 20 seconds, and then the depth of water started just above 19, so probably 20 centimeters. So this needs to go up to 20. This size, and I've not got enough room, so this is going up in fives. And then we just need to plot these and decide from our graph whether a linear model is appropriate. So we've got 0, 19.1, 10, 17.8 approximately there, as close as I can get, 30, 15.2, 60, 11.3, 100, 6.1, and at 120 we're at 3.5. So we can see that there's a line going on there. How good of a line are we seeing? Let's actually try drawing a line through them, starting there and going through, and we can see that's pretty much perfect for a straight line. So we can conclude the graph shows that the linear model is appropriate. In other words, it is appropriate for us to try and create a relationship of the form ax plus b. We've concluded that we are correct to use this form. Hence why part B says deduce an equation in the form d equals at plus b. Now you could do that from the graph. Look at your graph and come up with a gradient for that. But since we've got some accurate numbers, I couldn't plot this accurately in the table, in the graph rather. Using this table though, we could get our gradient accurately. So when this went up 10, this went down 1.3. So our gradient is negative 1.3 divided by 10. So our gradient is A. Negative 0.13. And then our B we have here. B is the y-intercept. So rather than using the graph and doing it fairly inaccurately, we can say that D is equal to negative 0.13 t plus 19.1. So a more accurate version for the model. Let's see, another one of these, interpret the meaning of the coefficients A and B. So A is similar to the one we had before. It's the change in depth for every increase in one time unit, which in this case is seconds. It's the change in depth every second. Okay, so for every second that passes, depth is going down by 0.13 centimeters. B is what the depth was when time was 0, so it's the initial depth. The initial depth of the water. Part D. Just do it here. Beneath this is just another copy of the graph. Part D. Use the model to find the time when the container will be empty. In other words, when the depth has reached 0. So 0 equals negative 0.13 t plus 19.1. So we've set the depth equal to 0, and we want to solve this to work out the time when this has occurred. So that will happen. Add the t to this side, then divide by the 0.13. We'll get 19.1 divided by 0.1. Which if you calculated that, we get 140 seconds. 147 seconds. Rounded to 3 significant figures, as we should round everything to. Okay, so we determined that a linear model was appropriate by plotting the graph. We could then change the information in the table into the equation, using the table rather than the graph so that we could be more accurate. Interpreting the meaning of the gradient and the y-intercept of the graph. And then we can make predictions using that model for any value we need. Okay, final example on modelling. It's about population. In 1991, we have 18,500 people. And then we have a prediction that this population will increase by 350 every year. A, we're writing a linear model, so we don't have a graph involved at all in this. Write a linear model for the population P. So P equals something to do with T this time in years. It's increasing 350 each year, so that's our gradient, that's our rate of increase. So 350t. And when t was 0, 1991 is our 0 point, our initial point. We had 18,500 people. So that will do as our model. Let's see why might this not be realistic? Well, just a basic knowledge of population change. If you know anything about population, you know that population increase is not linear. Any population of anything, whether it's animal, insect, human, we know that population doesn't go up. Negative anyway. Population does not go up by a straight line. It goes up exponentially. So we could say population is unlikely to increase by the same amount. Each year we can mention population generally increases exponentially. So an exponential model would be far more realistic than a linear model. Okay, and that's it for modelling of straight lines, and that's the end of this chapter. So you should now be able to try the exercises in 5H. That'll be about modelling. And then you could also try some of the mixed exercises if you want to practice a mixture of all the things that have come up in this chapter now.